Okay, so thanks for everyone for coming. This is going to be our first talk. So Professor John Marie Linhart from Central Washington University is going to share with us talking about transforming ODE education, integrating modeling projects to engage future mathematics teachers. Thank you.
Thank you for the introduction, Yangping. I'm going to drop a few things in the chat. So I'm going to drop a syllabus for the course into the chat. Let me see, what else am I going to give for you immediately? I'm going to give you the modeling project, the learning objectives. This is our detailed learning objective for the course. And I'm going to drop some stuff for the modeling project in the course in the chat as well, if that is something that anyone's interested in. I've got a few more things I could put in there, but I'll stop right there. So I'm at Central Washington University, and before this, I used to be at Texas A&M University. Texas A&M is a large engineering school. Maybe some of you are at engineering schools where you're teaching a lot of differential equations to engineering students. That certainly was also my background. But Central Washington University is not that school. We are a regional, non-selective, primarily undergraduate institution. We work on the quarter system, and our differential equations class is 3 quarter credits, which is the equivalent of 2 semester credits. So if you are at a semester school and you're like, man, you're not getting through much of my differential equations curriculum, I can't get through more of your differential equations curriculum because I just don't have that many class contact hours. Our differential equations class was probably created with the thought of math majors in mind, but at this point, it's primarily taken also by physics majors. There are a lot of physics majors in the class and secondary mathematics education. So that's our future high school teachers. And to be honest with you, we're suffering with enrollment like everywhere else in the country is. And our theoretical math major is gone, and applied math major is holding on by a thread right now. So, but where our secondary education is growing, so we've kind of got to keep those secondary education students in the class, or we're basically hearing a lot of death knells in there. And then that's going to affect other programs, because when you can only offer differential equations once a year, that makes it very hard for a student who has not been successful with the class to make it up. And it also makes scheduling harder for everyone. So getting a good differential equations course, getting students through it, keeping our secondary majors in there so that we can run it more often is just critically important to our long-term survival. And that brings us to the problem that secondary education majors, in some sense, need some different things out of differential equations than we think of the math majors as needing. Now, I think that actually it's going to help everybody if we do it this way, but let's think about where we're at. So our secondary education program very much promotes project-based learning, but in calculus and the lower level courses, we are not seeing project-based learning. Differential equations is one place, especially with the fact that we know that modeling and differential equations is a powerful learning tool where we can incorporate projects. Another issue that we have is that while some of us are into alternative grading and other innovative pedagogical techniques, many of our instructors are not. And so we would like to see our students experience some of these techniques, because there's a simple truth that teachers teach as they were taught. So if students have experience with projects and innovations, then they're more likely to embrace them themselves. And frankly, we need these students in our courses, or we're not going to be able to run these courses. So we really need students to see what I've got pictured right here, which is the mathematical modeling cycle. And this is from the Guidelines for Assessment and Instruction in Mathematical Education, Mathematical Modeling Education. That's a publication of COMAP, the Consortium on Mathematics and its Applications. So we need them to see that. So what happened was we entered a course redesign process, and fortunately we managed to keep some folks out of the course redesign project because I don't think they were going to help us out. But I and another math professor and a mathematics education professor, we all had experience, although not recent experience, in teaching differential equations. One of parts of my story is that I came here with a lot of differential equations teaching experience, but almost never taught the class because there were other instructors who kind of owned the class, and it was just, and I'm not going to fight anybody to teach a class. And I have tried, because My professional survival depends on it. I try to find areas where other people don't want to teach, and I'm going to go try to get as many courses like that as possible that I can teach over and over again so that I have more time to devote to other things. And that's part of my life is imploding right now because, of course, when we're offering classes less often, then I'm teaching 3 different courses every quarter, and man, that has been hard. So we had 3 people with differential equations teaching experience on the committee. And we sat down in part with the SIMIODE textbook, but also just kind of thinking to ourselves, what's really important in a differential equations class? And we wrote down some learning objectives, and we tried to be really clear about what was more important and what was less important. So our mathematics education person took on the mathematical modeling. My colleague in the math department, the other professor, took on the first order equations. I was a natural one for numerical methods. And then we all kind of talked a little bit about what we should do with second order equations. We have a detailed list, and then we kind of distilled that list down into what becomes our course level learning objectives. We agreed that we could add a week-long modeling project, and we're by and large in agreement with what our content goals were for the course. We are dumping some content out of the course. I'm not teaching solving first order equations by exact methods anymore. I'm not going to spend a lot of time on the existence and uniqueness theorem. Honestly, I've taught that content, and students have never done one, they don't understand why they're learning it, and they never have done well on it. So can we get something where they're actually going to take it away? And I don't know that it's that important, if they're engineers or physicists or whatnot. I'd rather have them remember the method of separation of variables, which, I teach mathematical modeling, and, I give them that exponential differential equation, du dt is equal to a constant times u. And I have students, every time I ask them to solve that in class the first time, look at me and say, we don't know what to do. I'd much rather have them say, yes, I know how to do this one, than have them, spend a week worrying about the existence and uniqueness theorem. So we distilled that down into 7 catalog level student learning objectives. So SLOs, the student learning objectives. And then we brought in our physics faculty and asked them what they would like or what comments they have. And they would like us to do more second order equations. And I have thus far maybe been disappointing them a bit because I just don't have time to do a ton right there. So if you're curious about our learning objectives, here they are for you. So you can see that we were pretty explicit in when we're talking about determining solutions to first order differential equations, that we're really talking about separable methods and the integrating factor for linear ODEs. The second learning objective, that's all the qualitative methods that you think of. I don't have time to do a ton with bifurcations, although I certainly got that material covered when I did this last quarter. Numerical methods, I think, are crucially important. To be honest with you, we do more and more work on computers. And it's always been true that if you met a random differential equation as if there was such a thing, that would not be something that you could solve by hand. So numerical methods are really fundamental. Second order differential equations, it's clear we're going to do linear constant coefficient second order homogeneous differential equations. But here we've got our modeling process goal made very clear in the catalog objectives. Use of technology, I think, is on everybody's catalog of learning objectives. But do we actually mindfully do that? I'm going to try, at least in my course. And communication appears again and again. And we're not always super mindful about how it is that we're teaching communication, but I am trying to be super mindful about that. So with these learning outcomes in mind, we did adopt the SIMIODE textbook. We're going through most of chapter 1. We're going through most of chapter 2. We're going through a lot of chapter 3, but not all of it. And we're certainly starting in on chapter 4. That's all we're going to get in the quarter. I do have students try to read the book. This is a learning objective that's one of mine, but it's also shared, I think, by other professors, that students benefit when they know how to approach reading a textbook. I didn't know how to do this when I was in graduate school. I remember my thesis advisor giving me papers and asking me to read them, and I get to some mathematics that I didn't understand, and I didn't know what to do next. And that really held me back for a long time. And I really needed somebody to sit me down and say, you're not going to understand everything. Get the big ideas out of this thing. Make yourself a dang outline of this. Try to get those big ideas. And when we need to fill in the details, we're going to fill that in. And so that's really what I'm emphasizing to my students. Write an outline, get the big ideas on. Once you've got an outline of what those big ideas are, then use that book and try the reading exercises. And then tell me, what big questions do you have? Where were you lost in the section? And what are you interested and curious about? And let me say, when I first looked at that SIMIODE textbook, no shade to Kurt Bryan, I think he's written a fantastic book, but I wasn't so sure of that when I started out. I was scared that students were going to hate this and that they weren't going to be able to get anywhere with this and that this was going to be literally a crap show. And it wasn't. I was shocked when students sat down to read this one Olympic 100-meter dash. They got really excited that they were seeing real applications. And if they got now they were unhappy because they also didn't understand all of the reading exercises. So we did certainly talk about that. But then the next section is about how do you deliver medication to the ear. And that was exciting too. And they're still not completely happy because not everything is easy. But at this point, I think I've got serious buy-in from them for the content of the course, which is amazing. And then when I get to section 1.3, which is a hard section, by the way, again, we're seeing real applications. Actually, it's section 1.4, not 1.3. Section 1.4, we actually get some important content that I missed in my prior courses, which is that in section 1.4, we learn how to solve differential equations of the form x prime of t is a function of t. So all you have to do is integrate. And that has been missed. And I have taught senior classes where I've asked them to solve motion under gravity with no air resistance. So you've got second order differential equations equal to either constants or zero. And I've asked students to solve them and had them look at me and say, you're crazy. We don't remember how to do any of this. I'm like, integrate, integrate. So now they actually get that practice integrating. And the reaction to section 1.5, which talks about dimensionality, I had a physics student look at me and just like eyebrows up and like, why don't they teach this in other courses? We need this material. Why aren't they teaching this to us? So I got a lot of buy-in from students. They do find it hard. Absolutely, they find it hard. But they believe that this course, the core material from the course matters in a way that they've never believed that before. So the next thing I had to do is heading a modeling project. And if you missed Thomas Clark's presentation at SIMIODE a year or two ago, please go look that up in the videos. It was a wonderful presentation, and please go get his paper from Primus. This is a beautiful little paper, and whether you use it in your class or not, you will be a better person from having read it. I cannot say enough good things about it. So Torricelli's law has to do with draining water out of various objects, and the first one, which I think is present in many ways on the SIMIODE repository, is draining water from the cylinder. Now, I love this project in a lot of ways. And the first thing I love about this project is that we can use our skills on dimensionality to verify that this law, that the fluid velocity is equal to the square root of 2gh, that's dimensionally consistent. And then the next thing I really love about this is that we get to use the chain rule. And I think the chain rule is just so important, and that students don't understand why it's important and how it's useful. So when we're applying this, so when we take Torricelli's law, we get the differential, the derivative of volume is equal to minus A0. So that would be the size of the hole from which water is going to drain times the velocity of fluid of the water. And if you think about it logically, that makes sense. It's dimensionally consistent. And then because we know the form that the velocity of the fluid takes place, We know that this is going to be some constant k times the square root of h. Then if we apply this to a cylinder, we've got the equation for the volume of the cylinder, but we have v prime of t. Well, v prime of t is dv dh dh dt, so we have to differentiate with respect to h. Now we're just going to get a constant times h. So you're unsurprised when I tell you that our differential equation in h is h prime is equal to minus some k mu k square root of h of t. Now one of the things students really like here is that like we get all these constants, or you go do the derivatives, you're going to find there's all these constants. And I'm like, well, just smash all the constants together, right? I'm a mathematician. I'm not going to go measure anything out here. So I'm not going to measure what the values of any of those are. So let's just call it a constant. We're going to solve for this at the end. And they're like, whoa, you can do that. And I'm like, yes, I can do that. So they're pretty excited about that. And this is a simple separable differential equation right here. They can solve this. So they do. And then I put the data into Desmos. They can use sliders on Desmos to try to find the value of the constant, and they do. And look at how well this matches the data. Is that just not great? Okay, success. First part of the project, 1 day done. Second day, we drain a cone. Same idea as before, same equations. And again, we get to use my favorite rule of them all, the chain rule. dv dt is dv dh dh dt. You'll notice from the equation from the volume of a cone that we have a little more dependent on h. We get a slightly more complicated differential equation, and we go try to match that to the data. And now it doesn't match quite so well. If we match these early data points, we have a lovely model that does not match at the end. And here's the next exciting thing that we get to do. We get to go back to this modeling process. We have identified and specified the problem to be solved. We've made assumptions. We've defined our variables. We've gotten equations. We've done the math. We've gotten a solution. Now we're analyzing and assessing the model. And dang it, we need to go back to our assumptions again. Yes. And when we do that, we discover that the water is not draining from the bottom of the cylinder. So we need to take that into account. So our volume equation becomes the whole volume minus this piece of volume we missed at the bottom. And we can go through, crunch through to get this differential equation for the height of the cylinder. We solve it, and now we're going to get an implicit solution that we can't solve for h of t, but when we can still match that to the data, and look at how we did. Is that not awesome? So go see Tom's presentation on this. He's going to go through a little more of the math, and he also does a sphere. I'm not going to get to the sphere. It is great stuff. So the students are, as we go along with each of these class days, giving me hand-ins, telling me about the mathematical work they did for that day. But one of the big things they hand in for the project is a reflection on the process of mathematical modeling. So summarize the work that we've done in this project in complete sentences without formulas. And as you do so, identify how you have seen the process of mathematical modeling in the work that we've done. And I try to always ask them, whether it's in their reading or other things, tell me what you learned, found interesting, or remained curious about. Because I think one of the things I really want students to think about is that you should be learning something. You should be curious about something. It's okay to have questions and to not know everything. The second project I added is mathematical communication. So I really wanted to make this communication business explicit. Professional communication is done by typing, so we are going to type up some mathematics perhaps for the first time for many of these students. Now, if they need to handwrite it, I will accept a handwritten communication project, but I tell them straight out, I'm not going to give you a grade higher than a B. And if you get an opportunity to revise, revising is easier if it's typed. So imagine you have a friend who's taking differential equations, clearly not from me, because their professor is kind of teaching them how to solve these first order linear equations by memorizing a bunch of formulas and a procedure. So instead, I want you to think about how that integrating factor works. and why it works. And I give them lots of examples of this in class. I also recorded a video of me doing exactly what I want them to do on this problem. So guys, we've got a video of that as well. So I really want them to think about, the procedure and about how you can understand the procedure and memorize nothing from here. I did write them a communication sample on the method of separation of variables. I emphasize, I don't want to see every step in you doing your integrals. Give some guideposts, but you don't have to show your reader everything. Your reader is somebody who's good at integrals. I do give them both an overleaf, so that's a LaTeX template, and a Word template that they can work with. And then I just simply give them links to videos that show them how to type mathematics with LaTeX and Word. And of course, I tell them I'm happy to see them and happy to help them if they're struggling to do anything there. Try to give them with about 2 weeks to work on this so that they do have time. And overall, I think it went pretty well. I was pretty easy in the first go around. I only had 12 students in the class, so that was easier for me for grading. It was pretty clear that there were students who kind of were getting at strategy and some students who weren't. By the way, I've improved this prompt here to kind of get at what I want to see a little bit more. So that kind of the first go through, I gave, about half the students B's and about half of them C's, and then everybody who made an attempt to incorporate feedback and resubmit got their grade raised up 1 grade level. I've got to say, I've been thinking about teaching writing and mathematics for a long time, and I don't think I can demand quality of my students. And so I've had to go back and think about what I care about. And what I care about is that they know that writing is a process, that we all start somewhere, we all make mistakes, and that if we work on things, we can make it better. So I'm really trying to emphasize process here over quality. There is some quality built into the grade, but it's not everything. So this quarter, I've got a lot more students than I did last quarter. So I'm going to try to give some quick feedback here, and then I'm going to ask them to do peer reviews of 2 other students for some more feedback before they review. The third project I incorporated is numerical methods. I like to work with Python. Part of this is because I've talked to my former students and asked what is valuable to students? What should I be doing that's really going to have payback for them? And Python was at the top of their list. So I gave, and I also have thought hard about, again, I can't teach them everything in a course like this. It's not a programming course. I don't have a lot of time to spend on this, but I do think that every exposure to true programming and good programming languages helps them when they have their next task to do. So anything I can do here is going to benefit them, even if it's not a lot and it's not perfect. So I give them a working Euler's method, and then I ask them to copy, paste, and modify to get improved Euler. And then once they've got a working improved Euler, they can copy, paste, and modify to get Runge-Kutta. And then they can look at what I've programmed for them in terms of tests and graphs to see how that works. And then I would like them to copy, paste, and modify to solve yet another differential equation, again, one that they can solve, so they've got a true solution there, and to make some more tables and graphs. So this is an example of the sort of graph that you've got. What I don't love about the graph, and will never love, is that improved Euler and RK4 are always on top of the true solution. Those are both really excellent methods. Now, when you look at a table of the errors.
Sorry for interrupting. We are kind of running out of time. So,
okay. So let me just finish up. You can really clearly see how the errors improve here. I asked them for a reflection on what they did. We do have 3 tests. I do allow students to retake or correct tests. I think that's really important. I've gotten some great comments on student evaluations. There are 4 comments here. I had 12 students in this class on the redesign on the fall. So you've heard from 1/3 of my class right here about how much they enjoyed the project. And that's pretty much what I have today. Thank you very much for being here. Thank you very much for listening. I hope I said something or gave you something that you can find valuable in one of your classes.
Thank you very much.